Projectiles, inclined plane, type 5, downhill. So in 2008 we had a particle that was projected down an inclined plane. So we need to make sure we underline down. And the line of projection makes an angle of 2 theta with the inclined plane. And also we would underline inclined plane and not the horizontal. And the plane is inclined at theta to the horizontal. We're told the plane of projection is vertical and contains the line of greatest slope. So they always say that statement in these, which just means it's projected straight up or straight down. It's not veering off to the left or the right. And we want to then show that the range of the particle on the inclined plane is given by ku squared sine theta over g. So of course we're not going to get ku squared sine theta over g. We're going to get something in terms of u squared sine theta over g, where k is a constant and we're asked to find the value of k. So it's the range that we're trying to work out in this question. So what we want to do is again draw our diagram. We're marking in the angle of the inclined plane is theta. And then we're told the particle is projected down the hill. And the angle with respect to the inclined plane is 2 theta. And the initial velocity is u meters per second. So we're going to draw our projectile path. And again, we know on landing, because it started on the plane and it's landing on the plane, then that Sy will be equal to 0 on landing. Now we have to be very careful here with our downhill. So we're going to just draw a little diagram to the side here for our gravity. Oh, that's really bad. So gravity is a little bit different in this question. So if I show gravity at any point on the projectile path, it's in a downward direction. We know that the inclined plane is theta there. Therefore, these two angles are going to be vertically opposite. And if I resolve my gravity with respect to the horizontal, so parallel and perpendicular, and again, I mark in my initial velocity in the y direction and initial velocity in the x direction. Well, what you can see is that gravity in the y direction is in the opposite direction. So therefore that's going to be minus g, and that's theta. So minus g cos theta. But it's in the same direction as u in the x direction, so it's actually going to be positive this time for the x direction for gravity. So if we fill out our table, again press pause, u, a, v, s and t, and you're going to work out your table in terms of u, a, v, s and t in the x and the y direction for me. So if we look in the x direction, we're going to have u cos alpha. So again, alpha in this case is your 2 theta and beta is your theta. So if we have u cos alpha, that's going to be u cos 2 theta. And in the y direction, that's u sine 2 theta. A resolved in the x direction, we saw there is going to be the g sine theta. So again, it's going to be positive. And of course, beta in this case is theta. So that's g sine theta, and then it's minus g cos theta in the y direction. So again, if v is equal to u plus at and s is equal to ut plus a half at squared, then resolving those in the x and y direction gives us u cos 2 theta plus, this time, g sine theta t. And v in the y direction is u sine 2 theta minus g cos theta t. And then s in the x direction is u cos 2 theta t plus a half g sine theta t squared. And in the y direction, u sine 2 theta t minus a half g cos theta t squared. And again, time in terms of t for both. Okay, so if we're looking for the range, then again, on landing we said sy is equal to 0. So this is our range here. It's our s in the x direction from start to finish. So in other words, to get s of x, we need the time of flight. And the time of flight then will be on landing, sy will be equal to 0. So we take our equation for s of y, which we said was u sine 2 theta t minus a half g cos theta t squared. And if I let that equal to 0, and then factorize out my t, multiply across by 2 first, get rid of my fraction. Then if I take out t as being common, I'm left with 2u sine 2 theta minus g cos theta t. So if they both multiply to give me 0, one must be 0 or both must be 0. And therefore I get t is equal to 2u sine 2 theta over g cos theta. In other words, the displacement is y, in the y direction is 0 at the start and also at the end. So this second one here is my time of flight. Now, of course, that time of flight can actually be simplified one step further, because we can see there that I have sine 2 theta. And we know in trig that in sine 2 theta, that's 2 sine theta cos theta. So again, page 14 in your maths tables will tell you that. And if I sub that in, well, that actually simplifies one step further to give me 2u, instead of sine 2 theta, I'm putting in 2 sine theta cos theta all over g cos theta. So how many of you forgot to spot that? And that will leave us then with 4u sine theta over g. Okay, so either of those would represent the time of flight, but at some point you're going to have to get rid of that sine 2 theta. Okay, so now we know our time of flight. We're going to sub in our range. In other words, s of x is when our time of flight is equal to 4u sine theta over g. Okay, so what did we say s of x was? Well, s of x was u cos 2 theta t plus a half g sine theta t squared. And we're going to replace t with 4u sine theta over g. But we can also see we have cos 2 theta. And we know from page 14 of our maths tables that cos 2 theta is cos squared theta minus sine squared theta. But I don't want to be putting in cos's and sines into the one equation here, because I can see my time of flight is in terms of sine, and my range I want to show, if I go back to the start, is only in terms of sine. So I want to get rid of anything to do with cos here. So we know from our derivations of cos squared theta minus sine squared theta that this can also be written as 1 minus 2 sine squared theta, because of course cos squared theta is equal to 1 minus sine squared theta. So cos squared theta plus sine squared theta equals 1 on page 13 of your maths tables. So I'm going to replace cos 2 theta there with 1 minus 2 sine squared theta. Lovely bit of trig in this question. Loving it. So we have 4u sine theta over g. And then we have plus a half g sine theta, and then we have to be careful here because we're squaring our time. Don't forget that it's t squared Okay, so a little bit of algebra here now, multiplication, multiplying everything out. So we have u minus 2u sine squared theta times 4u sine theta, and that's going to be all over g. And then I have plus g sine theta, and it's going to be all over 2 times 16u squared sine squared over g squared. Okay, so we're going to end up with a sine cubed here, and again I can see, well, 2 is going to go into 16 and g is going to go into g squared. I'm going to multiply the brackets here then again. So I have u by 4u is going to be 4u squared sine theta minus 2u by 4u is 8u squared. Sine squared by sine theta is going to be sine cubed theta, and that's all over g. Again, just keeping it in brackets to keep it neat. And then I have 2 goes into 16 8 times, so that's 8u squared, and sine theta by sine squared theta is sine cubed theta, and that is all over g. Okay, and now I can see I have a lowest common denominator is g, so I can add everything on the top line there. So 4u squared sine theta minus 8u squared sine cubed theta plus 8u squared sine cubed theta. Look at this. This is great. What looks like a mess is now going to tidy up because they are the same. And therefore that is really nice, because now we have just simply 4u squared sine theta over g. Now let's go back to the start. Well, we have to show that the range is ku squared sine theta over g. And look at that. We have u squared sine theta over g, which is our range. Hence, if I look, well, there's my constant. K is 4. Really nice. So where were our marks coming for in this question? Well, we had to look at the range. So the first set of 5 marks was for letting our sy equal 0. Second set of 5 marks, was actually for writing down what our sy is, and then letting it equal to 0 was 5 marks. Getting our time of flight was 5 marks. Getting s of x and subbing in our time of flight was 5 marks. And then getting k equals 4 was 5 marks. Okay, so we have one more thing left to look at in projectiles, which is bouncing, but we're not going to do that until we've gone through the rest of the course, and then we're going to revisit the kind of unusual questions in linear motion and in projectiles. So we'll come back to projectiles again at the end, okay?